The trick to being able to do this while it's live is just be quick with it. That's all. You only get probably a second, literally. Alright, cool. Alright, so these are what you call an 80% gas furnace. You can tell the difference between 80% and 90% just based off the flue pipe is going to be a first indication. See, that's going to be the galvanized metal there. They call that B vent. 90% furnace is going to have plastic. You're going to see like a white plastic PVC coming out of it. And the reason why is because the exhaust gases, they're not going to be as hot as they're exiting the furnace just because it's pulling that much more heat energy out of it. That's why it's called 90% plus, because it's pulling about 90% or more of the heat energy out of the exhaust gases. Okay, so the first thing we want to go ahead and do, oh sorry, did you have any questions on that? Because I'm probably going pretty fast.
Oh, that's all right.
My apologies. Yeah, let me know if I'm just going a little too intense, because I like to use this here. You could just use a regular K-tape. I don't know if you take any of these type thermometers on you in your bag, but hit it somewhere in like one of the takeoffs. Usually not, preferably not in the flex, because that could cause that flex to tear internally. It's got a, I know you did a little bit of duct work and you saw the lining is kind of, if you put a rip in that lining, if the static pressure is high enough, it could tear it. Use like a screw. Well, I'll just use my little drill bit. You can just cover this back up with tape. Put a tiny hole there, you know. Sometimes you'll even be able to hit it. Ay. It's the smallest hole right there. Simple. Boom. See what I mean? And what this is, we're checking what they call the temperature rise. Okay, so we'll start off with that. Remember I told you how you can check most of the stuff with the system still running? So that's one, right? Now we'll figure out, what are we working on, upstairs or downstairs? The quick way to know that is just see how these returns terminate. This is what they call a return run, meaning this is where the air gets pulled back. It's returning the air to the unit. That's why it's called return. So you remember where we saw the filter, where I asked them how old it's been since, how long it's been since you replaced that filter? Yep. That's the return register. Okay, that's why the filter's there, because it's filtering the air as it's being pulled back into the system. Then it gets there's a fan in here behind this door. We'll see that in a second, and that'll essentially will basically force discharge the air up through the evaporator coil and then through your supplies. That's supplying the air back to the house. Okay, sometimes they get confusing, but when you think about it like that, it makes sense why it's called a return and supply, right? And like I say, if you already know some stuff, you can let me know, because I don't know how much you know, how much you don't know, so I'm just kind of starting it off like basic. You know what I mean?
It's a review either way.
Yeah, exactly. This is one of the gas valves. Remember I told you, hey, 70% of the time you can check the gas with the system running? This is the one where you can't. Well, you can, but it's more dangerous. So you got these type of screws in here. You got to take those out, and it lets a lot of gas out compared to the other style. I'll show you. I'm going to check my amps on the inducer motor. This is the inducer motor. This was causing the exhaust gases. If you look down through here, you can see the flames.
Yep.
They're being sucked down into those holes. That's because this inducer motor has got an impeller in there, and it's pulling the flame up through pretty much a serpentine type heat exchanger, and then it's forcing it up through here. This is the outlet of the inducer out of the house. Okay, check my amp draw here. So we got a 0.48 on my inducer amps, and then this is a total amp draw. So that means this is basically the line voltage coming in, high voltage, 120 volts, and it's powering the whole furnace. So it's a cumulative voltage. So you see 2.74, that means it's capturing the blower amps and the inducer amps. So if I just want the blower amps, I'm going to subtract what I captured for the inducer amps. That makes sense? So I'm just going to go ahead and subtract the 0.48, yeah, 0.48, thanks, from, I've got what we call a manometer. You got any experience with this?
It's the static pressure.
Yes, sir. And yep, we could do gas pressure, static pressure. So essentially, I've got this here tip on here with the ball inflator. So I don't have to now drill any major holes in this thing. I can pretty much say zero it out. You always want to zero manometers to atmosphere. That means it's nulling any background, any pressures as it's in the atmospheric pressure. Now I'm going into a negative pressure zone. See that? So you've got 0.12 inches of water column negative. See the minus there?
Mm-hmm.
I'm just going to go ahead and push that. It'll capture that value. Now if I want to check my positive pressure, if you want total static pressure, this is important to capture. Total static pressure is going to be, let's think of a way to explain it. Static pressure is everything that's creating resistance of flow on this motor. So what I'm going to show you is this. We're going to hit right here. In order to get our total, I'm going to put a hole on the side of the furnace here, and I'll show you why here in a second. All right, so it's a quick tap right there. Now why I'm putting a hole here is because this coil is a resistance to airflow, right? There's going to be a coil in here that's got restrictive veins and, you know, fins in there that's restricting air from getting up past it, okay? So that's going to be what they call a positive static pressure. This is negative. So look, there's our positive static pressure, 0.34 inches of water column. So just imagine it like this. If I were to take this coil off and put a piece of wood on top of it, this static pressure would be off the charts. It would probably be like 2 inches of static pressure, okay? So that's just kind of like an extreme so you can get the idea of what's, and then if I were to take this off, take these off, and just put wood in front of that, then it would be the same. It would be 2 inches of negative static pressure. You see what I'm saying?
Yep.
So that's kind of, you know, whether people realize it or not, these are creating resistance to flow. There's ducts and, you know, everything that's put on top of this furnace or connected to the furnace is resisting the flow somehow, okay? If I take the filter out right now, you'll see that if I put the static pressure back on the return side, the static pressure will go lower because I'm taking a resistance of flow out. You got that? Ah, shucks. This only has to sit in there for maybe like, you know, 5 minutes or so. So we captured that, we apply that, 2 values captured. So that's done with that. We're still going to use this to check our gas pressure, but now I'm going to do a combustion analysis. This is a combustion analyzer. It's pretty much measuring, it's verifying that this is getting complete combustion, as complete as possible per the manufacturer's specification, that basically air and gases are mixing and creating a nice complete combustion. All right, so I'm going to go ahead and tap a hole here. You usually want to be about 12 inches from your, there she goes. Now we just take this thing, probe here. Hit start, and we're wanting to see, like O2 is oxygen. That means how much oxygen is in these gases, right? Mm-hmm. Pure oxygen. You want that to be between maybe 5 and 9%, something to that effect. CO, that's going to be carbon monoxide. That's going to be a deadly gas. I know you've heard of that.
Oh yeah.
So we want that to be below 100 parts per million. Stack temperature, that's the temperature of the gases exiting. So that's pretty much what that's gonna tell you how efficient the system is running. That's gonna help calculate efficiency. The hotter those gases are, guess what that means? The more heat is getting out of the house, the less efficient the system is, right? If I'm pulling, the more heat I can pull out of these gases before they're exiting, the more efficient the furnace is going to be. You want that to be between probably 380 to 450 degrees, something to that effect. Suffice to say, this is just going to be a nice way of, it's a way of testing the furnace combustion and how complete it's burning the fuel. So we got 119 degrees there, T1, T2. Pop this in here like such. That's going to get our temperature differential. Now you're going to see here on the nameplate, it's pretty important. Whenever you're doing maintenances, you want to study these nameplates, right? Temperature rise here, 40 to 70 degrees, and this piece of tape's on it, but I just know because that's, so between 40 and 70. So that means the difference in temperature of the air coming in here and the air leaving after the heat's been added to the air should be between 40 and 70. Now with an 80% furnace, you want that to be probably the middle to high, probably about 50 to 60. 90% you want it to be kind of the middle, medium to low range of the temp rise. So I'm just going to go ahead and let that stabilize a bit. I'm going to go ahead and check the draft pressure, which is the amount of draft. This is a negative pressure in here, meaning that the pressure in this pipe is actually lower than the pressure that we're standing in right now, even though the gases are being, the reason why is because it's actually it's inducing a draft in the flue pipe. It's not That's why it's called an induced draft motor. It's not pressurizing the pipe, it's just making it so that hot air is rising in there. Heat rises, so the velocity, the speed of that hot air rising is pulling in the air behind it, causing a negative pressure, if that makes sense. So we're just going to go ahead and hit start. We want to make sure our draft is probably between 2 and 3/100ths, maybe 2 and 4/100ths of an inch of water column. So we pop that in there like such. Always zero that to atmosphere, and we can see that's about, we'll hit stop and see where it stands, about 4/100ths of an inch of water column. That's a really good draft. Okay, and that's how you see 0.04. That's 4/100ths of an inch. Now we're going to go ahead and check our flame sensor. All right, so now we're going to check our flame sensor microamps, and that's going to be, see this here? This is connected to a wire that goes to your board, and it's going to sense the flame. It's letting the board know that there's a flame present in this here burner assembly. And the way it knows that is basically there's a rod that's pretty much immersed in that flame. It's pretty much rectifying the flame and creating a signal, a DC voltage, a small microamp voltage back to the board. So we're just going to get this here, put this in microamps, and we want it to be in microamps DC, not AC. And we're just going to put it in series, you know, just wire it, run it in series. But as you can see, the system is able to run a good long time while checking everything. So we've got our meter here, pop that there. Now the trick to being able to do this while it's live is just be quick with it. That's all. You only get probably a second, literally, to make contact with this other side. So I'm just going to go ahead and try to rush it. Sometimes it works, sometimes it doesn't. Oh, there it is. Got it. That's reading 3.3 microamps. Okay. See how quick I had to be there?
Yeah.
So we're gonna pop it back on. Oh, I missed it. No big deal. You see how fast it is. It doesn't take long. But I didn't need to pop it back on. It was ready to turn off anyway. We checked everything we need to check other than gas pressures. We're gonna clean that while it's off. And to clean it, you just want to simply clean it. We just want to go ahead and pull that screw out, just one screw usually. This thing just pulls out like such. So there we go. And I just keep this type of Brillo pad on us, okay? But this one actually looks pretty decent. A lot of times you'll see just a bunch of powdery white residue on there, but that's fine. Let's do a quick little clean like such. And that might actually give us a little bit more. A little more signal. We'll see. I'll test it again after the cleaning. Got that there. Turn our gas on. And then we'll put this in here. Let's see what happens. It's probably not going to be much more because it wasn't that dirty, but if it were dirty, you'd see a significant improvement. Yeah, no better. 3.1. So that's that. That all makes sense?
Yes.
Sweet. So like I said, once again, we'll illustrate what happens. See how that's in series? You know what a series circuit is? Mm-hmm. All right, cool. So that's running through the meter, boom, back in through. So that's what happens. That's why this, see, that's how long we have. We literally have a second to do it, but that's enough. It's plenty enough to connect the meter to the other side. All right, so check gas pressure. I use this here, this tool. It's like the Klein multi. And then I'm going to show you why I said this style gas valve is not, it's not really good to try to do this with the circuit open. Mm-hmm. Okay, so we'll just put this in here. So I've got the gas turned off here. I don't know if you noticed how I turned that off. Yep. So we're opening that up. That's why I've got that magnet on there, so that sticks. If you lose that, you're shot. You know, it's a bad day for you. I mean, it's not the end of the world, but so you see how this has got multiple different fittings. So this is here, this is a ball inflator. That's for static pressure. This here is for checking a different type of gas valve, which is you just slide this right over it. That's the one you can check live. And then the threaded brass fitting, that's for checking these. Okay. Go back to our app, zero it out, zero pressure. So simply just pop this on here like such, right? So I just reset it. This little switch here, open up this power. Now it's gonna, it pretty much faulted out. It attempted too many tries to recycle. So now it should cut back on here. Turn our gas pressure on, you're gonna see this number go up, right? Spike like crazy. See that? 40 inches of water column. That's pretty much because it was like it was static in the line, so now it just spiked it, but it'll go down. So we're checking both this side and this side. So what this side is going to be the pressure on this line here and back. That makes sense? Mm-hmm. And then this here is showing the pressure that's on this manifold here. Because what happens is there's little orifices that are on the other side of this here. You can't see it really now. Well, you can see it if you looked above and over it. And there's small little tiny, you see these brass pieces here?
Yeah.
So there's small holes in that are creating, because the gas isn't able to flow at the same rate as it's able to flow in here, wide open, that these restrictions are creating a back pressure on this line. So it's a little bit of pressure in here. Usually you want that pressure to be between 3.2 and 3.8 inches of water column. In this line you want to be between maybe 5 and 11 inches of water column. But no worries, because it will tell you on the data plate. So as you can see here, minimum for this line is 4.5 and 13. Okay, you can see that there. And then the nominal for this line is 3.5. And it tells you right there. So it kind of makes it foolproof or whatever. So this is super important as well. This ground should always be, make sure it's got a good connection, because if that ground's not properly seated, it'll have an issue trying to sense flame for the flame sensor. All right, so you're going to see this gas pressure drop as well. So that's so crazy. So essentially, it's right now 8.5. By the time the gas valve opens up, it's going to probably drop down to about 7.8, something to that effect. So there you go. And that's because the pressure on the line before was static. Now it's flow. That's flow pressure that you're seeing now. So it's always going to be a little less. Okay. So we'll go ahead and capture that. You don't want to over tighten these, because that's just an aluminum body. You know what I mean, on the gas valve. So just snug it up. Okay. I'm glad it gives you so many attempts. And now we got the manifold. This is called manifold pressure, right? Don't need to go crazy on that, just a quick snug. So we see we got nothing there now. Gas valve, gas pressure's on. Now she's going to give us a little something. So we're looking for about 3.5 inches of water. Here she goes. 3.55, 3.56. Apply that. So we've pretty much finished this system, realistically speaking. Now it's going to be a lot of visual inspection, you know. Okay, so yeah. So basically with the thermal imager, what I'm trying to do here is I'm using it to inspect the ductwork, do like a really rough inspection. And what it is like, as long as you see the heat's contained within the ductwork, you don't see the heat like spread out all into the attic and stuff like that. 9 times out of 10 there's not going to be any large cracks or anything like that. All right, so we're not seeing any crazy spread out hot zones. Everything seems to be pretty well contained in the duct, right? But yeah, this is a pretty slick image, just the top down. TC003. We'll do the same over here. I just want to make sure And like I said, this is kind of, it's not necessary, don't get me wrong, but it helps to be a little more efficient, right? I don't have to go out there putting my hands on every duct necessarily. I'm just looking for really blown out hot spots. I could demonstrate, maybe one day I'll demonstrate what it looks like so you can see, so you'll know. But just know that it'll just look like the heat's escaping, you know, the really high bright orange parts will be escaping out of the duct, and it'll be all in the attic area or all on the roof, something to that effect.
Is that just a patch job, or is that a full replacement?
Oh no, you just be able to patch it up depending on how bad the ductwork. Now if the ductwork is all old and that's why it did that, then yeah, it would be a whole replacement basically. Okay, or a duct replacement at least. You wouldn't have to replace the system. Check us out here. It's another thing. So this is a way to visually inspect the unit. I had one not even a couple weeks back as well, where it was a zone system and it was pretty shoddy duct board plenum. This is a plenum here. That thing, that's a plenum. That means it's the part that's the runs are coming off of. See how you got a bunch of, and that plenum got blown out. The top of it was completely blown off. You can see massive amount of heat escaping. So right now that top looks legit. So I don't have to sit there and go up there and look, right? Just make sure all your takeoffs and everything are looking good, not crazy heat escaping from around the takeoffs. Simple. Make sure you don't have crazy heat escaping from the coil. You know, just basic general visual inspection. But that's that. So that right there completes, and we could have done that before we turned the system off, so that's one more thing you could have done with that, with the system running. All right, that's it. That's beautiful. The reason I cut the gas off before I open this up is you always want to make sure that that heat exchanger has ample enough time to cool before you open this door and shut the power completely. You hear that blower still running? The inducer's still running, as you can see. What that's trying to do is basically cool off the heat exchanger before the system turns off. Because if you don't, if your system cuts off, all the blower and all the inducer cuts off, that heat exchanger is going to still be hot as crap. And it could potentially cause stress cracks and things like that. So I let that run for a bit, just cool it down. Now we let it shut off. Okay. So now blower inspection. We can now check and see, okay, that's going to be an ECM motor, meaning that it doesn't have a capacitor to check. Okay, so that's cool. And then we also want to check the blower wheel. So I'm just going to pop this off. Maybe pop this. And I usually use my phone. It's probably still turning in there. No, it's not actually. Cool. Yeah, I can see it there. It looks good. Check out that diamond-shaped duct they put in. That's pretty interesting, huh? Like I said, make sure visually check and see it. But you can also feel. See how I'm feeling in there? Feeling the blade. That feels crispy. It feels clean. If you feel like grit and stuff like that pulling up off with your fingernails, then that's shot. You probably want to let them know, hey, this needs to be clean. The blower needs to be clean. Give them the price on that. Because it's pretty important. That blower wheel, it can have the smallest amount of dirt on it, and that will affect the airflow significantly, just based off of the not even having much dirt on those fins there. So that's it. You know, make sure the pan and everything is on there solid, not letting the attic air come up in through here. Because imagine sometimes this pan could be loose or disconnected, and all summer it'll be pulling attic air, 150-degree attic air up into the return, you know. So these are all things we need to always be looking out for. Another thing is this, boom. Always like to clean these out. See this here?
Yep.
That orange hose. Ugh. You want to kind of push down on it first and twist it just that way it doesn't break the darn thing. 'Cause a lot of times it just heat welded onto there, sort of. Jeez. Sucker. See, sometimes if it's not broke, don't fix it, because otherwise you'll wind up screwing around and messing something up and be here longer than you need to be. But the reason that's coming off. Sweet. So you see there's a little port there.
Yep.
Now what I'm going to do with that, I usually keep like a wire that'll fit in there, but thermostat wire or something. If this here gets blocked up, it's going to stop making negative pressure. See this pressure, this switch here?
Mm-hmm.
This is what they call a pressure switch, and that's going to be letting the furnace know, letting the board know that this inducer is running. So if this gets clogged up, this holes, then essentially it's not going to pull in the diaphragm in this pressure switch in order to make contact in these two lines here to let the board know we got a draft inducer running. So that's pretty important to keep that cleaned out. One of them, it used to be, like, not so much anymore, but a few years ago that used to be one of my major furnace calls, is having that get clogged up. Usually for units in crawl spaces, that's going to be a big deal.
Mm-hmm.
Because just the environment under the crawl space, the conditions in there. That's it for that unit. Any questions or anything like this?
Oh, I'm good so far.
Nice. Let's move on to the next one.